Automatic Generation Control, AGC, is a critical real-time closed-loop control system used in interconnected power systems worldwide. Its primary function is to automatically maintain system frequency at its nominal value, typically 50 Hz or 60 Hz, regulate interchange power flows between control areas, distribute generation changes economically among participating units, maintain tie-line schedules, and coordinate generator load changes based on demand fluctuations. The fundamental principle of AGC is ensuring that generation equals load plus losses continuously, thereby maintaining grid stability and power quality. In modern power systems, AGC has become increasingly important due to the growing complexity of electrical networks, integration of renewable energy sources, and the need for precise control in deregulated electricity markets. Without AGC, any load change would disturb system frequency, tie-line power flows would deviate from scheduled values, generators would respond unevenly, and overall system stability and reliability would be compromised. AGC restores balance automatically within seconds, maintaining grid stability and quality even under fluctuating conditions. Components and levels of control in AGC. AGC systems consist of several key components working in coordination. 1. Load frequency control, LFC, loop, monitors system frequency and adjusts generation accordingly. 2. Tie-line control loop, manages power exchanges between interconnected areas. 3. Area control error, ACE, computation, calculates the deviation from scheduled values. 4. Governor speed control, primary control provides immediate response to frequency changes. 5. Automatic controller, secondary control implements the AGC strategy. 6. Supervisory control, tertiary control/economic dispatch optimizes generation costs. These components operate in a hierarchical control structure with 3 distinct levels. Primary control, governor, operates in milliseconds to seconds, stabilizing frequency immediately through proportional response. This is the first line of defense against frequency deviations and is implemented locally at each generating unit through governors that adjust mechanical input to the turbine based on frequency changes. Secondary control, AGC, operates in seconds to minutes, restoring frequency to nominal value and eliminating ACE. This level adjusts unit set points and distributes generation changes among participating units based on economic participation factors. It uses ACE as the primary control signal to determine how much generation adjustment is needed. Tertiary control, economic dispatch, operates in minutes to hours, optimizing generation cost and reallocating reserve. This level uses economic dispatch algorithms to determine the most cost-effective generation mix while meeting all system constraints and security requirements. Area control error and frequency bias factor. Area control error, ACE, is the key measurement in AGC, representing how much a control area deviates from its tie-line schedule and nominal frequency. The ACE formula is AC equals P underscore tie actual P underscore tie is schedule plus B F underscore actual F underscore nominal. Where P underscore tie actual equals actual tie-line power flow. P underscore tie schedule equals scheduled tie-line interchange. F underscore actual equals actual frequency. F underscore nominal equals rated frequency. B equals frequency bias factor, MW/Hertz. When ACE is positive, it indicates that the area is taking more power than scheduled, and the area should increase generation. When ACE is negative, it indicates that the area is exporting more power, and the area should reduce generation. The goal is to keep ACE at 0 on average. The frequency bias factor, B, expresses how much a control area should change its generation for a 1 Hz frequency deviation. Typical values are 1% to 2% of capacity per Hertz for 50 Hz systems, with larger systems often using doubled bias control, plus or minus B, to improve stability. A properly tuned bias factor ensures that each area responds proportionally to system frequency deviations, preventing oscillations and maintaining stability across the interconnected system. AGC modes of operation. AGC typically operates in 4 primary modes, each designed for specific operational requirements. 1. TLBC mode, tie-line bias control. This is the most widely used mode in interconnected power systems. It controls generation using ACE equals tie-line error plus frequency bias, maintaining both frequency and tie-line schedules simultaneously. The purpose is to keep ACE as almost equal to zero over time, ensuring that the control area neither takes nor exports more power than scheduled while contributing to overall frequency regulation. 2. CFC mode, constant frequency control. In this mode, AGC adjusts generation only based on frequency deviation, while tie-line flow schedules are ignored. This mode is primarily used in island operation or during system separation events, such as black start procedures, island microgrids, or emergency operation when maintaining system frequency is the priority. 3. CNIC mode, constant net interchange control. This mode controls tie-line flow to match scheduled interchange, while frequency deviations are ignored in control action. It is used when maintaining contractual energy schedules is critical, particularly in market-based systems with strict interchange rules and financial penalties for deviations. 4. Manual mode, in this mode, AGC is bypassed, and operators adjust generation output manually. This is typically used during maintenance, testing, or emergencies when automatic control may be inappropriate or when specific operational strategies require direct human intervention. AGC operation and applications. The AGC operation follows a systematic 5-step process. 1. Measure, system frequency, tie-line power flows, and unit outputs are continuously monitored. 2. Compute ACE, using the bias factor in tie-line deviation, the ACE is calculated. 3. Generate AGC command, AGC determines how much generation change is needed to eliminate ACE. 4. Dispatch to units, AGC sends signals to governors, turbines, and generator setpoints, with participation factors ensuring economic sharing. 5. Units respond, generation changes until ACE approaches zero. Modern AGC systems have numerous applications in today's power systems. Integration of renewable energy sources, AGC helps balance the variability of wind and solar generation. Smart grid implementations, advanced AGC algorithms enable more responsive and adaptive control. Cross-border power trading, AGC ensures compliance with international power exchange agreements. Microgrid operation, specialized AGC strategies enable stable operation of isolated power systems. Emergency response, AGC provides critical support during system disturbances and recovery. In conclusion, AGC is an essential component of modern power system operation, ensuring stability, reliability, and economic efficiency. Understanding AGC principles, including ACE calculation, frequency bias factor, and various operational modes, is fundamental for power system control engineers and grid operators. As power systems continue to evolve with increasing renewable penetration and market complexity, AGC systems will continue to play an even more critical role in maintaining the balance between generation and load.